Hello everyone, welcome to a fresh new lecture on the topic Z transform, and this is part of the course Signal Processing Algorithms and Architectures. I am Dr. Anirban Dasgupta and let's get started. So, what is this Z transform? We already have a transform in the frequency domain, which is the Fourier transform. So, Z transform is another transform which converts my discrete time signal x of n into a complex frequency domain representation, and this is kind of the analogous to the Laplace transform for continuous time signals. So, in Laplace we extended the concept of continuous time Fourier transform from a single j omega axis to the S plane. Similarly, here we extend the concept of Fourier transform or the discrete time Fourier transform to the whole Z plane. So, why do we need Z transform? So, this is very useful in analyzing linear time invariant systems, specifically with respect to stability and other properties, and also it is useful in solving difference equation like Laplace was used to solve differential equations. This is useful in solving difference equation. What is a difference equation? Suppose I say y of n is x of n plus some 2 times x of n minus 1 and so on, and there can be also terms of y of n minus 1 as well. So, these kind of equations are called difference equation, and this is the discrete time counterpart of differential equations. So, for a discrete time sequence or signal x of n, we will define the Z transform x of z as summation from negative infinity to positive infinity over the index n x of n z power minus n. So, here what is z? So, z is a complex variable, and usually complex variables or complex numbers are represented as a real axis like x and something like j y axis as the y axis. But here we are more interested in the polar representation than this Cartesian representation, and the polar representation is in the r omega form, where r is the magnitude and omega is the phase. So, whenever you go radially outward from the origin, your r will increase, and that is the representation of the magnitude of the component, and the phase or the omega will vary from 0 to twice pi via a rotation. Okay. So, now how do we interpret that? This is what I was talking about. So, we have this z plane, and these are the values of omega, where this angle is my 0 degree, right up the y axis is my pi by 2, the negative x axis is my pi, and the negative y axis is omega equals to 3 by 2. So, this is again just an extension of the DTFT throughout the plane. So, DTFT is typically, if you see, this is the evaluation at the unit circle. So, this green line is representing the unit circle denoted by mod z equals to 1, and this, say I have a number which is lying on the unit circle, that is the evaluation of the DTFT. So, you can see or compare these two formulas. So, x of z and x of omega, which is the DTFT, you see they are very similar, and if you compare these two, you will clearly see that the DTFT is evaluation of the Z transform, where z equals to e power j omega or the unit circle. So, why this is needed? Now, as we know that Fourier transform are not defined for all signals, specifically if that Fourier summation is not finite. So, in this case the Z transform is defined, and this is defined for almost all signals, but not over the whole Z plane, but in a specific region, and this region is called the region of convergence. So, clearly when mod Z equals to 1, this is the unit circle in the Z plane, and the Z transform will reduce to the DTFT. So, what is the region of convergence? The region of convergence is those values in the z plane where the z transform exists, or in other words, whether the formula of summation converges and gives a finite value. Now, clearly the ROC will never contain any poles. You know what are poles? So, if you represent the system as a transfer function yz by xz, so where xz equals to 0, which will make this transfer function infinite, these are the poles, that location of those z. So, ROC cannot contain poles because ROC will be those points where the z transform has finite values. So, ROC is crucial in determining the properties of the system or the signal which is being analyzed. Like for example, if we have a causal signal, now causality is mainly described in terms of systems, but causal signals are also defined for signals which are right sided, like for xn is 0 where n is less than 0, this kind of signals are called causal signals. So, in such signals the ROC will extend outward, like if I draw a circle, so ROC will be somewhere like outside some circle, and this is defined by the outermost pole. For anti-causal signals, signals which are left sided, so in those signals it is inside some circle, the ROC, and if the signal is two sided, that means there are positive indices as well as negative indices of n, the signal exists. In such cases, the ROC is typically an annular region, that is the region between two disks, difference region. So, we will understand each of these meanings, but let us try to see this pictorially, and we will start with finite duration signals. So, if it is a causal signal, causal means the values are 0 for n less than 0. So, here we see that the entire z plane is the ROC except the point z equals to 0. Why so? I will explain. For anti-causal signals where the signal values are 0 for positive values of n, here the entire z plane is the ROC except z equals to infinity. And if it is a two-sided finite signal, like having values for both positive and negative indices of n, then the ROC again will be entire z plane except z equals to 0 and z equals to infinity. Now, what about infinite duration signals? So, infinite duration signals will also have a very similar pattern, but here instead of just the origin, we will have a disk, and this infinite and finite will play a major role in filter design and implementation, where we will discuss about FIR and IIR filters. But as of now, if we see this, so if I have an infinite duration causal signal, a right sided signal, then the ROC will be some outer circle, like region beyond a circle, like mod z greater than R2. And if it is an anti-causal signal, the ROC will be contained within some circle like this, mod z less than some R1. And finally, if it is a two-sided signal, like having values for both positive and negative indices, it is kind of an annular ring like this. So, let us try to break this down and clearly understand that why this is happening in such a manner. So, we will start with an example of a finite signal which is causal. So, this is our signal where this 3 is my 0 index, or I would say that x of 0 is 3, x of 1 is 6, x of 2 is 8 and so on. So, how do I calculate the z transform? I will use the formula, but the formula says minus infinity to infinity, but I know that the sequence will not exist below negative 1 or below 0, I would say. Also this infinity you can write, because after index 3 everything will be again 0, because this is a finite length sequence. So, if I plug in the values, so first value is I put n equals to 0, I get x 0 which is 3, and z power 0, then x1 which is 6, then z power negative 1, then x2 which is 8, then z power negative 2, and then x3 z power negative 3, and rest are zeros, and then z power 0 is 1, and so I can expand this in this manner, 3 plus 6 z inverse plus 8 z minus 2 and 7 z power minus 3. Now, here we clearly see that this is a polynomial in z inverse. So, if I get a value of 0 for z, then that z inverse term becomes infinite or undefined, and the transform will not exist. So, the arrow C cannot contain z equals to 0, which is defining my first concept. Similarly, we can define it for the finite anti-causal signal, and this is the example. So, here my 0 index is 6, and these are all negative indices like n equals to minus 1, minus 2 and minus 3, and I will quickly plug in the formula, and here my values again, although it is from minus 3 to 0, I can say minus infinity to 0 just to show that it is an anti-causal signal, and I will plug in the values, and let us see what I get. I get this expression. You can verify this. So, there are all positive powers of z. So, here if I put z equals to 0, it is not an issue, but z equals to infinity will be an issue, and hence z cannot contain the value infinity, either positive nor in negative infinity, and this is so clear. And I think by intuition the other thing will also be clear, but still let us take an example. So, this is my index 0, this is index 1, 2, 3, and these are indices minus 1, minus 2, minus 3. So, again if I put on the formula, and again since this is a two-sided signal, I am putting from negative infinity to positive infinity. I plug in the values because outside this range everything is 0. So, this is what I get, and clearly we see that at z equals to 0, this goes to infinity, positive infinity, and at z equals to infinity, either positive or negative, this term will go to infinity. So, the z cannot contain the infinity or 0 for the z transform to exist, which means the ROC is the entire z plane apart from these two parts. So, these are examples of FIR system or finite impulse response systems. Now, infinite causal signal, these are examples of filters which are of infinite length. So, here there will be a denominator part and there will be some poles. So, let us take an example. So, our xn is, so here I am talking about signals, but when I talk about poles, these are respect to systems, but I am not specifying here a signal or a system. I am in general, I say I have a sequence represented as x of n and I want to find the z transform. Now, of course, for signals Fourier is a better method, while for systems z transform is a better method. But in this case, just for introduction to z transform, let us assume that this is a function, this can be signal or a system, and this is defined by a power n u of n. So, the z transform will be, if I plug in the formula, and again I have said that there is a u of n. What is u of n? U of n, as we discussed in the first lecture, if you remember, this is 1 for n greater than equals to 0 and this is 0 otherwise, which makes it a right sided or causal signal. And now we see that this is a geometric series, because if I plug in the value of n, this is a power 0 z power minus 0, then n equals to 1 a power 1 z power minus 1, n equals to z power minus 2. So, this is a sequence which is of infinite length, infinite GP series like this. And we know that if I have an infinite GP series of the form r equals r to the power n, then the output is a by 1 minus r. So, a is the first term basically, which is r to the power 0. So, it makes it 1 by 1 minus r in this case. So, what do we get? So, here this will converge to this provided mod r is less than 1, because even if mod r is equals to 1, so I have infinite terms which are 1, so that is infinity, and if that is greater than 1, it will diverge and explode to infinity. So, only way if mod r is less than 1, then only the sequence will converge and you will get a finite value. So, here my r is a into z power minus 1. So, if this is negative, then only the sequence converges. So, which if you just put it and simplify properly, so mod z is greater than mod a, and this is nothing but the region outside this circle which is having radius a, and this is the z transform z by z minus a. Now, I will put a box in this formula because we will reuse this in my next slide, and I will take another example which is an anti-causal signal and it is also infinite here. So, minus a power n u of minus n minus 1. So, if I do the maths, I plug in, so this is the minus, this is the transform, and again here what I do is I just make a small change, that I put a new variable m which is minus n. So, here what happens is my summation of m now becomes 1 to infinity, and this pretty much looks like the previous case where I have this r here is a inverse. So, this r is the r for the GP series, r power n, which is right, n is this. So, now how will I solve this? I will put the formula and I will see that this will exist only if this value A inverse z is less than 1, and if I rearrange, we will see that mod z is less than mod A, which is the region inside the circle having radius a. My drawing may be not to scale or bad here, but I hope you have understood the concept. So, now if I just plug in the formula, I get this value a by 1 minus r, and if I rearrange things, I get z by z minus a. But hang on, in the previous case also I got the same z transform, and here also I got the same z transform. So, which means like Fourier, where two signals, two sinusoids having same frequency but different phase, the magnitude spectra was same. Here also we see that two different signals are having the same z transform. So, how do we distinguish them? So, we distinguish them only by the ROC, like this is the same signal, not the same signal, but the same z transform, but the ROCs are different. So, z transform does not just mean this expression for x of z. Z transform is the collective thing of this expression x of z and the ROC. This complete thing is called my z transform. Let us take another example where we will calculate the transfer function. Now, transfer function is a very trivial thing, and in this case we have a discrete time system. So, here we call it a pulse transfer function h of z, which is nothing but the ratio of y z by x z. So, this is a difference equation and this is an IIR system. Why so? I will explain later while talking about filter design and implementation. So, if you see, if I take the z transform of both sides, y n gives me y z, this is a constant, and z transform of y n minus 1 will be z inverse y z. Why it is so? This is a property. So, I am introducing a delay. So, delay in the time domain will be a z inverse multiplication in the frequency domain, and x n will give me x of z. And if I just arrange them, so what do I get basically? So, I get this expression. So, y z in terms of x z is this thing, and again if I bring down x z towards the left side denominator, so I get y z by x z, which is my transfer function to be this. So, if a system is defined in time domain by this difference equation, in the frequency domain or the z domain, the transfer function can be described by this. Let us take another example where the output is a advanced version of my input x of n plus 3. So, I have to find y of z in terms of x z. So, if I again take the z transform of both sides, so what happens is I get y z, and this I will not use the relation or any property, but rather let us use the formula. So, here I will put n plus 3 to be a dummy variable m. So, my n will become m minus 3, and I will get this. I bring out z power 3 outside. So, what I get this, and let us try to evaluate. So, here what I get is z cube, and then what I do is, if I take out the terms z power 0 and minus 1, this should be I think negative 3, n is m minus 3. So, what happens is, so if I take out, so I get the x 0 z power 0 which is 1 and x 1 z power minus 1. So, this is the expression which I get. Now, unless this x of 0 and x of 1 are zeros, you cannot find this transfer function. Now, take this as an exercise and think whether this system is a linear time invariant system or not, and under which circumstances it will become a linear time invariant system, or is it always a linear time invariant system. So, now we have understood the forward z transform. Let us think about the inverse transform. Like I have the x of z, I want to get back my time domain signal. So, this is given by the contour integral based on the Cauchy integral theorem, which is 1 by 2 pi j, this closed contour integration, and since x of z is a continuous thing, we are doing integration, but in the forward x of n was a discrete thing. So, we did summation. So, this is the equation, and here the contour will encircle the origin and lies within the ROC. So, basically this is the evaluation in the ROC of x of z. So, I will end this topic with some properties, and first property is the linearity property, which I have defined for most of the transform. So, if you see, if x 1 n gives you capital X 1 z and x 2 n gives you capital X 2 z, then if I multiply, I do a linear combination of these two, I get the same linear combination at the z transform domain as well. Similarly, time shifting. So, if I right shift or delay the signal by some amount k samples, it is multiplied by a factor z power minus k, just like e power minus j omega was multiplied in the case of Fourier omega k. And similarly, advancing the signal or left shift will result in z power k multiplication. So, convolution, and convolution multiplication is a very well known property for most of the transforms. So, only thing is that you have to remember when you have to use the circular convolution and linear convolution. So, here if we do linear convolution in the time, it is equivalent to multiplication in the z domain. Two more interesting properties of z transform is the initial value theorem, which states that if I know my x of z and I am just interested in the initial value of the signal, which is small x of 0, I do not need to do the whole entire inverse z transform. I just need to find the limit x of z when z tends to infinity. Similarly, if I want to find the final value, so this is the final value theorem, that limit x of n tends to infinity is limit z tends to 1 z minus 1 x capital X of z. So, this is the definition of the final value theorem for a stable system. So, I will conclude with some common Z transform pairs, like for the discrete time sequence delta n, which is always 1 in all the transforms which we have covered. So, here we have 1 and the ROC will be all Z, and probably this is the only sequence where you have all the ROCs where the whole Z plane where the transform is defined. What about U of n? This is a very well known case which we saw, like an extended version which we saw. So, it is Z by Z minus 1 or 1 by 1 minus Z inverse. The ROC is Z greater than 1. And another signal minus U minus n minus 1, which has the same Z transform, at least the x of Z, but the ROC will be different. Then delayed impulse delta of n minus k. So, this will give you Z power minus k, and if k is positive, then it will be the entire Z plane except Z equals to 0, and if k is negative, it will be the entire AZ plane except Z power infinity, and that is very easily seen from the transform. Another is 1 by n, where n is positive. So, here we get minus log of 1 minus Z inverse, and this you take as an exercise to find out using the formula, and here the ROC will be mod Z greater than 1, because this is a right sided infinite, not in, yeah, it is kind of infinite sequence. So, here it will be Z mod Z greater than 1. So, we will end here. Thank you so much. Have a nice day.